Okay, welcome to part 3 of negative feedback. So this is from chapter 22, part 3. Okay, on negative feedback. Okay, so previously we talked about transient times. Let me have a look. Transient times, reduced gain, and accuracy. And linearization. And so the next thing is sensitivity. So the question is, what happens to the sensitivity if we add negative feedback? And what we were talking about was this little thing here, y out. We have a gain, feedback of gain value k, or strength k, and I have a yn going in, there's the arrow there. So that was the feedback system. And the question was, if we add a negative feedback, how does the system, is the system more or less sensitive if we make perturbations, to the internals of the system A, or even to disturbances at Y out, okay? So the way to do that is pretty straightforward. So first of all, we need to write down the, let me see, make sure I got this right. Oh yeah, here we go. So what we need to do is, first of all, we write down the what y naught is a function. So it's y naught equals yi times a times 1 plus a k. So that's the feedback relation, okay, which you've seen before. All right. So the question now is, for example, what would be the case? And the key, what would be the case if we changed A, okay? So what I really want to, so what I'll do is I'll call this thing here G, okay? For the that's the gain of the entire feedback system. So why don't we ask the question, what is that? What is that derivative? So we can take the derivative of that, and we will get 1 over 1 plus a k squared. And that's the absolute sensitivity. If we wanted to go for the relative sensitivity, which a lot of people tend to go for, all I have to do is scale this by G and A, okay? That's all I have to do. In fact, I guess we could do it. So 1 over 1 plus AK squared. So multiply by A and divide by G. And we know G is 1 plus AK over A. So those cancel, that cancels. So I end up with 1 over 1 plus AK. So the point of that is that the loop gain, which is the key factor in a negative feedback loop, as that increases, the sensitivity drops. So as AK goes up, the sensitivity goes down, which is exactly what we would like. Okay, so that means any internal variation in A. Okay, so if this were an op amp, right, there may be some component variation, or if you're a living organism, there might be some genetic variation. That would alter slightly A. If there's negative feedback, any of those changes will have fairly minimal impact on the sensitivity of the system. Okay, basically the gain. All right, so the gain remains relatively constant so long as the loop gain is high enough, right? Which is where we get the negative feedback from. You can do the same thing with a disturbance. If you apply the disturbance to the output, all right, that basically turns into a summing junction here as well. If you do that, I mean, I suppose I can write down what the equation looks like. It'll basically look like y0 equals AYI, which we had before, divided by 1 minus AK. Then there's a minus D, which is part of the entire thing. So this is the disturbance. And I can, again, just compute the derivative. Well, in this case, I'll compute the derivative of y0 because that's what I'm interested in. How is y0 affected by disturbances? Okay, so I differentiate this equation with respect to d, and I get minus 1 over 1 plus ak. And again, you see that the sensitivity reduces as the loop gain goes up. All right. So this thing is also resistant to disturbances on the output. Now, this is particularly relevant, for example, if this were a voltage coming out of the op amp and you hooked up another circuit to your op amp that put a load on your op amp circuit, that would reduce y0, but the negative feedback will ensure that the y0 gets restored at least to some degree. And so the system is fairly immune to disturbances in y0. All right. So that's basically sensitivity, what's called static sensitivity. Well, yeah, static sensitivity, and it's for this particular model. Okay, this particular model here, which is fairly generic. All right. What happens if we have a system, a specific system? So let's say we had this system. Okay. And that's V1 or V2. And we want to know, well, how sensitive is this system to, say, changes in V1 or V2? There may be inputs here. We may have an enzyme there and an enzyme there. I want to know how sensitive is, say, X to changes in E1 and E2. Now, we know that the frequency response at 0 is, in fact, the sensitivity, right, with respect to some input, maybe E1. Okay. So what we need to do is basically to compute this term here. So we can do that. Well, actually, the one I've got in the book is the flux one, which I guess we could do. Yeah, let's do the flux one, though. So the flux one, okay, gives me the sensitivity of, say, E1 or E2. Sorry, gives me the sensitivity of the flux, i.e. the pathway reaction rate through this system, and we can find out how that flux is influenced by, say, E1 and how sensitive it is to E1. Now, the Hj expression was dV is a bit of a mouthful. I'm doing the short version here, okay? Minus n without, I'm setting s to 0, okay? So we don't have s in there. And n dV dp plus dV dp, right? Where p is your input. So in this case, we have a one-dimensional system. N is just that, the stoichiometry matrix is that. The dV by dx is dv1 dx, dv2 dx. Okay. Let's assume two inputs to the system, E1 and E2. Okay, we'll assume two inputs. So the dV by dP is, okay, so now the number of reactions R is 1, or is 2, N is 1, Q is 2. Number of inputs is 2. So this matrix here has to be a 2 by 2, okay, 2 by 2. And I know the top left corner will be V1 dE1, but I know that E1 does not affect V2 directly. And I also know that E1, or rather E2 does not affect V1, so that's that one. But I do know that E2 affects E2. So I end up with a diagonal matrix like that, okay? So I can enter these terms into this, into this equation here, okay? I can enter all those there, take the inverse. The inverse is easy because it's just one dimensional and is 1. And what I end up with is h of j0 equals quite a big matrix, and I'll just do one of these entries divided by, so that's divided by the determinant of the Jacobian. Okay, and then there's one here. There's another term here, another term here. Okay. This one, let's write down what each of them refers to. This one refers to dj1 de1. Sorry, this should be a total derivative. E1. This one refers to j1 de2. This one refers to j2 de1. And this one refers to j2 de2. Now, I've mentioned this before, but in this pathway, we only V1 equals V2 at steady state. So the flow at steady state, which we refer to as J, these are equivalent, equals J2, okay? All right, that is a sort of but this thing here is a sideways equivalent symbol. So those two are equivalent. So in fact, these two rows are identical, okay? Because they refer to the same flux. So dj1 de1 will be the same as dj2 e2 because j1 and j2 are the same. All right, at steady state. So I only have to look at one of these, and let's go and look at one, shall we? So let's look at this one. dj1 de1 equals dv2. So I'm taking this this piece here, dx dv1 de1 all over dv2 dx minus dv1 dx. Now it's more interesting to scale these. Okay, so we'll scale these. So we really want to scale this, and what I want on the left-hand side is that. So that's the scale version of the left-hand side, and I need to do the same kind of scaling on the right-hand side. So let's have a look here. So let's separate these out a bit. So the first thing I know is I multiply both sides by E1. Okay, so I'll put the E1 there. And we've got this. And then we've got V1 dx. I'll multiply top and bottom by x. So that doesn't change anything, okay? And then the other one is the V1, V2. Now, as I said before, V1 equals V2, which is the same as J1 and J2. So actually, if I divide all sides by J1, that should be J1, J1. That's as if I divided by V2, or in this case, V1, and up here, J1, V2, sorry, okay? That's the same thing, and I guess I might as well do this one here as well, I suppose. V1, okay? That's probably the only tricky thing you have to think about is that the two rates or the two fluxes, it's getting smaller, are the same. So whether I divide by V1 or V2 in these places is immaterial, okay? They're the same numbers. These are all the same numbers. V1, V2, J1, J2, they're all the same numbers. So I can just treat them as if they're the same. So now I basically have my scaled version. So this thing, so let's do this one first. This one becomes epsilon 2x. This one is the enzyme elasticity E1E, and we know that's 1, so I won't put that in. The denominator becomes E2x minus E1x. And then this thing here, right, becomes the scaled canonical transfer function at zero frequency, or the biologist will tell you it's the flux control coefficient. Okay, which is probably more of an official term, actually. So what this expression tells me is, it tells me how sensitive the flux of the system, the flow of material through the system how sensitive it is to changes in E1. I can do exactly the same thing for E2. And in fact, for E2, I will get, it's very similar. In fact, the denominators will always be the same because they come from the same determinant, okay? But the numerators will be different. And so that's the second one, okay? So that's the second one. So now we can do some, we can look at these equations and see what we can figure out. So let's draw the pathway here. That was the pathway, negative feedback. That was E1, E2. So that's the elasticity 1x. That's the elasticity 2x, okay? So let's say, first of all, there's no negative feedback, okay? So no negative feedback. So what does that mean? That means that E1x will equal 0. So if E1x equals 0, this piece disappears, this piece disappears, this piece disappears. So in that case, CJ1 E1 equals, well, these two cancel then in that case, equals 1, okay? And CJ E2, well, it's 0 because this top piece here is 0, so the whole thing goes to 0. So without negative feedback, all the sensitivity is focused on E1. There's nothing on E2. Now what happens if we add negative feedback, or let's say include negative feedback? Okay, we include negative feedback. What happens then? Well, in this case, I'll make the second one E2x first order, which is okay. The C1x, what about that? Well, it's negative feedback, so it's going to be less than 0, okay? So we have to remember that it's going to be less than 0. So let me write the control coefficient equations down here again. So CJ1 E1 equals, what was it? E2x over E2x minus E1x, and EJ1 E2 equals minus E1x over E2x minus E1x. Okay, so let's make this really, really negative. So we have a very, very strong negative feedback. So that's this term here. Okay, well, let me put that in there. So that's thing there. That's this here. That's this here. So we'll make it really, really negative. So this is negative, but there's a negative here, so that becomes positive. The same thing happens here. That's negative, so the whole thing is positive. So the whole thing is actually positive. And if it's big enough, it dominates that. And so essentially they cancel and we get 1. All right. The CJ1 E1, this one here, if this is very negative, so this is negative, but this is negative, so the whole thing is positive. So if that's really, really big, this one tends to 0. All right. So now, let me summarize that then. So that's without feedback. That's with feedback. So the sensitivities will be 1, 0, 0, 1, at least in the extremes. Okay. So that blue is a bit, it's not very, bit dark. Okay. So these are the two extremes. With feedback, all the sensitivity ends up outside the loop. With feedback, sorry, without, let me say it again. With feedback, all the sensitivity ends up in the step outside the loop. And without feedback, all the sensitivity ends up in the first step. So this has some, and in fact, this will apply to any length pathway you wish to make. I mean, if you do, let's say you do, let's do a few steps, so something like this, okay, and then you put a negative feedback around here. In this case, and you have 4 enzymes, all the sensitivity on the flow and the flux will be on the last step. There'll be very little sensitivity on the first step, second step, and the third step. Most of the sensitivity ends up on the last step. So this is some repercussions for drug targeting. If you wanted to design a drug target for this pathway, okay, where would you design which step would you target? Well, you'd have to start, you should, unless you have other information, you would target the last step. You never target, I mean, unless your drug is like a sledgehammer and basically turns the entire pathway off because it basically removes the first enzyme. Unless it does that, if you want a more subtle drug which has fewer side effects, you don't target the first step. Okay, you always target the last step. Right now, as I said, if you have a drug that's like a sledgehammer, you can target any site you like and it'll have an effect. But also there'll be lots of side effects which might not be good for the patient. So I mean, in the ideal situation is to have targeted drugs that you don't have to administer in large amounts. All right. If you don't administer in large amounts, you won't have the side effects, but you still get the effect you want on the phenotype. Okay, let me see what else we got here. Yeah, I think that'll do for then, for this part. Part 4, then we'll talk about stability, okay? So I'm going to turn off this one and then upload it to YouTube. Okay.